Today we are going to discuss the shear strength of soils. In fact, we will cover this topic in two parts, and this is the first part of the shear strength of soils. So, the shearing strength is the most important engineering property. While in this lecture, basic concepts have been discussed in detail to develop a real feel about the shearing strength. You will have to go through these all topics to develop a firm understanding about the shear strength. Text of the lecture is self-explanatory and you would be able to understand all these things very easily. The only thing which is required from your side is your concentration. Uh, in fact, in the next lecture, we will discuss some advanced topics of shearing strength. As I mentioned earlier, that basic topics have been elaborated in this lecture. Moreover, direct shear test and triaxial tests are discussed in detail. So, uh, additionally, you would find many solved problems in this lecture. So you will have to go through all that with the maximum level of concentration. So first in this lecture you would find the review of the basic concepts, normal and the shear stress along a plane. So you can see here this is the element of the soil, the normal stresses and the shear stresses are shown on that soil element. And here you can see that element again, and here we are considering this plane, this particular plane EF, and on that particular plane the normal stress which is acting, that is sigma n, and the shear stress that is acting on that plane is tau. So analytically we can determine sigma n and the shear stress on that inclined plane by using these equations, equation 1 and equation 2. Here you would find the principal planes and the principal stresses concept, and this is the equation number 3, and which will give you theta p, the angle of the principal plane. So keep this thing in the mind that there are two planes that are at right angles to each other on which shear stress is 0. So those planes are called as the principal planes, and the stresses which are acting on those planes are called as the principal stresses. So such planes are called principal planes, and the normal stress acting on them are termed principal stresses. And you are familiar with the major principal stress sigma n and the minor principal stress sigma 3. So you can see here the equation for the sigma n and the tau n, the normal stress and the shear stress acting on an inclined plane which is making an angle of theta. So there are two important points which are written over here. I would like to discuss those points over here. So whenever shear stress on any plane is 0, the plane is called principal plane. This plane has either the maximum principal stress sigma 1 or the minor principal stress sigma 3. For planes with major and minor principal stresses, the value of shear stress is 0. Now here on this particular slide you would find some information about the maximum shear stress, and to get the maximum shear stress we can use these equations, equation number 10 and equation number 11. So in brief, if you just look at the various equations, which were present on the previous slides, the equation number 1 to equation number 11. So we could find normal stress on any plane sigma n, shear stress on any plane tau n, angle of principal plane theta p, major principal stress sigma 1, minor principal stress sigma 3, angle of tau max plane, that is theta p dash, maximum shear stress, normal stress on plane of tau max. Well, this thing must be noted that the analytical procedure is sometimes awkward to use in practice. Now we will discuss a graphical procedure which will enable us to find the above without the hassle of going over many equations. So let's consider the graphical method representation of state of stress. Well, here by considering this equation, this one, a graphical approach can be developed. In fact, it was developed by the Mohr. Well, there are some important points. When the circle of equation 15 is plotted in tau sigma space, it is known as the Mohr circle of stress. I'm sure you are familiar with the Mohr circle. It represents the state of stress at a point at equilibrium, and it applies to any material, not just a soil. So that's why you would find the Mohr circle's application even in the structural analysis, the structural mechanics. Mohr circle is a two-dimensional graphical representation of the state of stress at a point. The scales of tau and sigma have to be the same to obtain circle from equation 15. The equation 15 I showed on the previous slide. So this point is very, very important, that the scales of shear stress and the normal stress have to be the same to obtain a circle. The Mohr circle construction enables the stresses acting in different directions at a point on a plane to be determined, provided that the stress acting normal to the plane is the principal stress. The normal stress and shear stress that act on any plane can also be determined by plotting a Mohr circle. Well, this slide is meant for the sign convention in Mohr circle. So, basically Mohr circle is being drawn by using this equation. And if you just look at this element again, so you can see that here sigma x is acting, here sigma y, and again this sigma x is acting, and here sigma y. So obviously this is in x direction, so that's why sigma x. This is in y direction, that's why this is sigma y. Now as far as the shear stresses are concerned, so first look at that. This is tau xy and this is tau xy. So two parallel equal, you can say, forces are there. Because of that the shearing is there. So you can see this is tau xy, this is also tau xy. Because you can see that this is present on that particular face on which sigma x is acting, that's why x is there, and y is that one because this is the y direction. Similarly, if you just look at this one, this is tau yx, and this is also the tau yx. So you can see that this is present on that particular face which is on which the sigma y is acting, and this is present along the x direction, that's why x subscript is there, so tau yx. Well, the important thing is the sign convention. When you are considering the normal stresses, compressive stresses are considered as positive in geotechnical engineering, or you can say the soil mechanics, and tension will be considered as negative. Now, as far as the shear stresses are concerned, counterclockwise rotation, when you are having counterclockwise rotation, positive sign will be used, and clockwise rotation, negative sign is to be used. Now look at this thing. This is a Mohr circle. Basically, this is the axis which is meant for the normal stress sigma, and this is the axis meant for the shear stress tau. So to plot the Mohr circle, what to do? First of all, try to mark this point. This point you are getting from this one, sigma x and tau xy. You can see sigma x, this is positive, so that's why you can see that we are using some values over here, okay, this point. And tau xy, if you just look at this one and this one, you are having anti-clockwise or the counter-clockwise rotation. So this is also positive. So that's why you can see tau xy is positive, sigma x is positive, so you have got this point. Similarly, you can consider this point. I mean, so this set sigma y and tau yx. Sigma y, you can say the compressive stress, again positive. But if you just look at the tau xy, this one, or even you can say this one, this can also be written as tau xy, no problem at all. So you can see this one and this one. Because of that, you are having the clockwise rotation, so negative sign is to be used, so minus tau xy. So that's why we have got this point and we have got this point. So just join these 2 points through a straight line. It will cut the horizontal axis somewhere here, so this is the center, and now you can draw a circle, and this is the Mohr circle. So it's very easy. If you are uh, having the real feel about the sign convention, so it's very easy to draw the Mohr circle. Now this slide is meant for the construction of Mohr circle. So first step is plot sigma y tau xy as point M, this one. Then plot sigma x tau xy as point R, this one. Connect M and R. Draw a circle of diameter of the line RM about the point where the line RM crosses the horizontal axis. Denote this as point O, this one. The points R and M in figure B above represent the stress conditions on the plane AD and AB respectively. O is the point of intersection of the normal stress axis with the line RM. Now here you would find some important points. The circle M and QRS drawn with O as the center and OR as the radius is Mohr circle for the stress conditions considered. The radius of the Mohr circle is equal to this. The stress on plane EF can be determined by moving an angle 2 theta, which is twice the angle that the plane EF makes in a counterclockwise direction with plane AB. In a counterclockwise direction from point M along the circumference of the Mohr circle to reach point Q. The abscissa and the ordinate of point Q respectively give the normal stress sigma n and the shear stress tau n on plane EF. You would find the detail of this particular point on the next slide. Because the ordinates, that is, the shear stresses of points N and S are 0, they represent the stresses on the principal planes. The abscissa of point N is equal to sigma 1 and the abscissa for point S is sigma 3. Now here look at that, a special case. As a special case, if the planes AB and AD are major and minor principal planes, the Mohr circle for such stress condition is shown in figure 10.3b. The abscissa and the ordinate of point Q gives the normal stress and shear stress respectively on the plane EF. So you can see here that just by considering this angle 2 theta, you have got this point, and this point will give you sigma n and the tau n. So next we will see a more powerful method for finding stress on any plane. So basically, if you just look at this particular case again, this is sigma 3, this is sigma 1. Major principal, this is minor principal stress, this is the major principal stress value. We want to know the normal stress and the shear stress on this particular plane, which is making an angle of theta with this surface horizontal. So what to do? From this, making this point O as reference, just measure the angle of 2 theta. Look at this angle, this is theta. So just considering 2 theta angle, just draw the line from the center to this. So in this way you will be getting this point Q, and that point Q will give you the normal and the shear stress on this particular plane here. Okay, now we are going to discuss the pole method for finding stresses on a plane. So this is very interesting, and I need your attention over here. There is a unique point on the Mohr circle called the pole, or the origin of planes. This point has a very useful property. Any straight line drawn through the pole will intersect the Mohr circle at a point which represents the state of stress on a plane inclined at the same orientation in space as the line. The concept means that if you know the state of stress sigma and tau on some plane in space, you can draw a line parallel to that plane through the coordinates of sigma and tau on the Mohr circle. The pole then is the point where the line intersects the Mohr circle. Once the pole is known, the stresses on any plane can readily be found by simply drawing a line from the pole parallel to that plane. The coordinates of the point of intersection with the Mohr circle determine the stresses on that plane. I will demonstrate this procedure on the next slide. Now look at this particular soil element. We are interested to know the normal stress and the shear stress on this particular plane EF. The procedure that we have discussed earlier, uh, first you will have to draw the Mohr circle. You will have to mark this point and this point. Just draw this line, and then you can draw this Mohr circle. Now to get the normal stress and the shear stress on this particular plane, one way is that you can measure the angle 2 theta, and then you can draw this line, and this point will give you sigma n and tau n. But if you just follow the pole method, in that method what to do? From this point you will have to draw this line parallel to this space, and from this point you will have to draw a line parallel to this. So in this way you are getting one point on the circumference of the circle, which is called as P, or the pole. Now if you just look at this line and make it as reference, so now just consider angle theta. So draw this line, so you are getting the same point, that is giving you sigma and tau n. So this is basically the pole method that we have just discussed. So from a point of known stress coordinates and plane orientation, draw a line parallel to the plane where the stress is acting on. The line intersecting the Mohr circle is the pole P. So this one. Okay, using the pole to determine principal planes. When you are you want to know the principal planes. The principal planes are those planes on which sigma 1 and sigma 3 are acting. Now, when you have drawn the Mohr circle and you are considering the normal stress, the principal stress is sigma 3 and the sigma 1. So obviously, this is sigma 3 and this is sigma 1. So we can draw the Mohr circle like this. Now, when you have located the pole, from this pole, just draw a line passing through this particular point, because this particular point is giving you the value of sigma 3. And from the same point, this pole, draw this line which is passing through this particular point, because this is sigma 1. This is representing sigma 1. So you can see that this angle theta p, this is the angle of the plane theta p, where so you can say that this is the angle theta p, and this is the direction of major principal stress on which sigma 1 is acting, and this is the direction of minor principal plane and sigma 3 is acting on that. So in this way you can use this technique to determine the principal planes. Then you would find some examples. Examples have been solved step by step, so you can go through all these problems. Remarks are also given, so you must go through all these remarks. I can skip these things and you can go through these examples yourselves. Okay, here the failure criteria of the soils have been discussed. There are many ways of defining a failure in real materials, or put another way, there are many failure criteria. Various theories are available for different engineering materials, however no one is general for all materials. The one generally accepted and used for soil is Mohr theory of failure, and you are quite familiar with that. According to Coulomb relation for shear strength, tau F is equal to C plus sigma n tangent phi, where sigma n is the normal stress on the failure plane. From the previous slides, we know how to estimate sigma n, but we still need to know the plane of failure. What is the failure plane? That is very, very important question. Is it the plane with the maximum shear stress? The answer is no. Is it the plane of the maximum normal stress, that is the major principal stress? The answer is no. You would find the answer on the next slide. So you will have to look at the Mohr theory of failure. Mohr theory of failure states that a material fails along the plane and at the time at which the angle between the resultant of the normal and shearing stress is a maximum. That is, when the combination of normal and shearing stresses produces a maximum obliquity angle alpha sub m. So this is the key sentence. So the answer of the question that was asked on the previous slide, you are getting it from here. when the combination of normal and shearing stresses produces maximum obliquity angle sigma alpha sub m. Now to understand this, look at that. This is the Mohr circle, the half circle is shown. So you can draw the half circle, that would be enough. So from here you can see that if we draw a line, this one, which is touching this Mohr circle at point T, so you can see that this angle is the angle of maximum obliquity, that is alpha m. So you can say that failure will occur if you are having the stresses, normal stresses and the shear stresses corresponding to point D. So you would find some more detail of this Coulomb, this Mohr failure theory on these slides, and then Mohr's failure envelope. So you can see here by plotting Mohr circles for different states of stresses, and in each case draw a tangent to each circle from the origin, we come up with points 1, 2, 3. If we connect these points, we come up with that what is called Mohr's failure envelope. So this is the Mohr failure envelope, this one. So this envelope separates cases of stresses which cause failure. For instance, if the normal stress and shear stress on a plane in a soil mass are such that they plot as point A shown on the previous slide, shear failure will not occur along that plane. For point B, failure takes place and point C cannot exist since it plots above failure envelope, and shear failure in a soil would have occurred already. Therefore, failure occurs only when the combination of shear and normal stress is such that the Mohr circle is tangent to the Mohr failure envelope. Then once the point of the tangency is determined, the angle of failure plane and the stresses sigma and tau can be determined using the pole method. So in this slide you can see the Mohr-Coulomb failure criterion. The disadvantage of Mohr failure envelope is that it is curved line and needs a lot of tests to construct and difficult to use. It was then approximated to be a straight line, and the equation for the line was written in terms of the Coulomb strength parameters C and phi like this. So this gave the birth to Mohr-Coulomb failure criterion, which is by far the most popular criterion applied to soils. So you can see here we are considering this one as the Mohr-Coulomb failure envelope. So this slide is meant for the orientation of the failure plane. So you can see that this is the Mohr circle, this is the pole. So you can see that if you just look at that, this dotted line, it is passing through this particular point and it is making an angle of theta f, where I mean to say this is the angle of the failure plane, because this point is lying at this particular point, which is you are having the link, or you can say the connection between this failure envelope and this Mohr circle. So here you can see the Mohr circles and failure envelope in terms of total and effective stresses. You are familiar with the total and effective stresses. You know the total stress means the effective stress plus pore water pressure, but you know the effective stress means total stress minus pore water pressure. So in that case you can see that this one in terms of total stresses, and this is in terms of effective stresses. So obviously this envelope is the failure envelope in terms of total stresses, and this one would be the failure envelope in terms of the effective stresses. So in this way, some more detail is provided about the Mohr-Coulomb failure envelope. So look at this one. What does failure envelope signify? So look at the points, point A, point B, and point C. If the magnitude of sigma and tau on plane AB are such that they plot as point A, shear failure will not occur along the plane. This is the point A. Now look at the point B. If the effective normal stress and the shear stress on plane AB plot as point B, which falls on the failure envelope, exactly on the failure envelope, shear failure will occur along that plane. This is this one. Then look at the third point. A state of stress on a plane represented by point C cannot exist because it plots above the failure envelope, and shear failure in a soil would have occurred already. So this is not existing actually. So you can see here two more circles, X and Y. So you can conclude this thing that Y is stable because this circle is not touching the failure envelope. But as this circle is touching the failure envelope, it means the failure will take place. So in this way, you would find some further information regarding the Mohr circle, the failure envelope in this. So you will have to go through these slides yourself. But if you just look at the remarks which are given over here, which are very important. C and phi are measures of shear strength and are called shear strength parameters. The parameters C, phi are in general not soil constants. I will repeat, the parameters C, phi are in general not soil constant. They depend on the initial state of soil, for example, density, water content, and type of loading, drained or undrained. In case of using effective stress, C' and phi' are called effective strength parameters. The values of C' for sand and inorganic silt is 0. For normally consolidated clay, C' can be approximated at 0. Over consolidated clays have values of C' that are greater than 0. So this point is very, very important. So now to onward, you would find the information related to laboratory shear strength test. There are different laboratory tests that we can perform, but in this lecture you would find the detail of direct shear test and the triaxial shear test. So you can see here some detail of shear test. You are familiar with that. So this test has been discussed in detail, so you will have to go through that. Advantages and disadvantages are also given, and then examples. And then you can see the triaxial test. So triaxial test is a very, very important test. So it has been discussed in detail. And here I would like to mention the two ways for applying axial load in the triaxial shear test. Application of dead weights or hydraulic pressure in equal increments until specimen fails. Application of axial deformation at a constant rate by means of a geared or hydraulic loading press. This is a strain control test. So in this way we can divide the triaxial test in two types. Number one, strain control test. Number two, stress control test. So if you just look at the stress control test in a strain control test, the test is conducted in such a way that the shearing strain increases at a given rate. Generally, the rate of increase of the shearing strain is kept constant and the specimen is sheared at a uniform strain rate. The shear force acting on the specimen is measured indirectly using a probing ring. The rate of shearing strain is controlled manually or by a gear system attached to an electric motor. Most of the shear tests are conducted as strain controlled. The stress-strain characteristics are easily obtained in these tests, as the shape of the stress-strain curve beyond the peak points can be observed only in a strain control test. A strain control test is easier to perform than a stress control test. Now look at the stress control test. In a stress control test, the shear force is increased at a given rate. Usually, the rate of increase of the shear force is maintained constant. The shear load is increased such that the shear stresses increase at a uniform rate. The resulting shear displacements are obtained by means of a dial gauge. Stress control tests are preferred for conducting shear tests at a very low rate because an applied load can easily be kept constant for any given period of time. Further, the load can be conveniently applied and removed. The stress control test represents the field conditions more closely. So in the following slide, you would find the detail of the triaxial shear test as the laboratory setup. So you can go through it and then look at the types of the triaxial test. So different types of tests are available: CD test, CU test, UU test. You know, you are familiar with that. You have performed such type of the test in the laboratory at the undergraduate level. Unconsolidated undrained test. CU, consolidated undrained test, and CD, consolidated drain test. So details of all these tests are given, so you will have to go through all the slides, and the information is provided in a systematic manner, so you could be able to understand all these mechanism involved in the different types of the triaxial test. So you will have to go through that. The things have been explained in a systematic manner, so you will have to go through it, all these slides, and then you would find the examples. So all these tests have been discussed in detail: UU test, CU test, and the CD test. So at the end, the UU test has been discussed in detail. and at the end you would find some more problems, examples, solved problems related to triaxial test. So in this way, we have discussed the basic concepts of the shearing strength, and we have discussed the Mohr circle construction in detail, and at the end of the lecture you uh, have seen the detail about the direct shear test and the triaxial test. Thank you.